Okay, in class tomorrow, we're going to be working through this. I actually will have a cart, um, two carts. Okay, this will be my X and my Y. I'm basically able to simulate exactly that in person. I can do it in person. These are my motion detectors, and this is a motion detector. Okay, at the end, and they're pointing towards the two carts. Okay. So they can actually determine the position of cart X and Y with respect to time, with respect to those motion detectors. So we will play with that and kind of look at that graph. This is an explosion, okay? This is an explosion, essentially. And these two carts start at rest. So the momentum is 0, and they will take off. This velocity would be to the right and this velocity would be to the left. And in an explosion, momentum is conserved. Momentum is change in momentum is conserved. It is the opposite of an perfectly inelastic collision, right? An inelastic collision, they run into each other and stick, and in an explosion, they split. It's going in the opposite direction. So what we're doing in class tomorrow is we're going to play with that system. I'm going to show some graphs because what can we get? We can get a position versus time curve. And so let's talk about cart Y. It has position wherever it started at, and then it will change, and cart X will, and this will be my velocity versus time graph, sorry. All right, so I can get those velocity versus time graphs from my motion detector. And then essentially those momentums will equal 0 because if the initial momentum was 0, the final momentum of the system must be 0. So A, state the basic physics principle or law that the students could use to determine the relationship of the momentum of the X bar system and the Y bar system. What do they mean by bars? These carts have bars that you can add to them, so you can add mass. And so we will keep the total number of bars the same, but we can move it around between cart X and Y. So I can have 4 bars total, and I can put maybe 2 on each. I can put 3 on one and 1 on each. I can put, anyway, the total number of bars I will keep the same. So what is the physics principle? The physics principle is conservation of momentum. Okay, so you can write conservation of momentum. You can say change in momentum of the system equals 0. You can write momentum initial of the system equals momentum final of the system. All 3 of those are basically stating the principle, which is momentum is conserved. Using the principle, and I personally might say because no external forces to the X, Y cart bar system. Okay. All right. Using the principle or law stated in A, so now I'm doing double I, AI, determine the equation for the relationship of the momentum of the cart X bar system to the momentum of the cart Y bar system immediately after the recoil in terms of quantities that can be obtained from measurements. Okay, so momentum initial, not A, momentum initial of X plus momentum initial of Y has to be equal to momentum final of X plus momentum final of Y. This is 0. So 0 equals momentum final of X plus momentum final of Y. The negative of momentum final of X, actually didn't have to even do that. I could just say, I can't measure momentum. I can measure mass and I can measure velocity. So I have mass of x times final velocity of x plus mass of y times final velocity of y. I can measure those, all of those. I can leave it just as it is, or I can move them uh, to one side or the other. Oops, equals. Okay, that will get you full credit. You started with an equation. I want to determine an equation. This is an old problem. Now they would probably say derive, okay, because we're starting from first principles. Okay, now here we go. Design an experimental procedure that the students could use to determine the relationship of the momentum of the X bar system. I want to determine the relationship. So some type of equation, some type of relationship. An equation is a relationship of the momentum of the X bar system to the momentum of the Y bar system immediately after recoil. So we have to actually, you have to, in my opinion, you need to have a sketch so that you can show what you're doing. Okay. You have to think about all the things that we need to measure. We need the mass of X. I want mass of X cart, and it would be mx. Scale. Mass of Y cart bar, and it is my. It is scale. We need to measure velocity final. We don't have to measure velocity initial because it is 0. And that, oh, I'm getting them mixed up. So it is velocity final of X, and it would be VFX. And we will use the motion detector. Velocity final of Y, and we will use the motion detector. Anything else that we have to measure? I don't think so. Okay, we have to have a procedure to be used, and we have to refer to the table, and we have to discuss it in terms of the symbols that we used. Okay, so I'm going to have to, I wonder if I can add a page here. Can I insert a page? Yes. Add a page. Perfect. Good. So procedure. All right. So one of the things is, again, it is best if you have a drawing because you want to refer to your sketch in your procedure. Okay. So 1, and your table of data. Measure mass of X cart and Y cart. Using, you have to say what you're doing using scale and record. Okay. Set up per sketch motion detectors to determine position versus time for cart X and cart Y. So if you have your motion detector, this is your detector, and even if you had your kind of symbol, so it's pointing towards X and Y, okay? Place cart X and Y on track on level track, okay? The track needs to be level, on level track. And record position versus time using motion detectors just before, during, and after. So it's got a little spring and there's a plunger. Plunger is released, or spring is released, maybe spring. Spring is released, okay? Four, use data to calculate velocities of X and Y after spring released. This is a point right here. Number 5 is 1 point. To reduce error, repeat steps 3 through 4 several times, typically at least 3 times. So we want 3 runs, and average data. Okay, so we're going to have an average velocity. Blah, 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 blah. Okay. Number 6. Add bars to cart X. Repeat steps 3 through 5. Number 7, maybe add bars to cart Y. Repeat steps 3 through 5. Okay, so we've moved the masses around and we can develop a relationship between momentum of the carts compared to their masses. Okay, personally, it's a very poorly written question. Lots of physics teachers can't stand this one. I'm using this mostly to get you started thinking about how to collect data, how to do a motion sensor, and so forth. Okay. All right, let's go back to the question. So that's kind of a procedure. All right. How would you graphically analyze the data from the procedure in part B? So I want to know, how do I graphically look at this data to determine a relationship of this, the experiment? So how do I graphically develop a relationship? I would have momentum of Y versus the momentum of X for each one. So if I had and you can plot it. So that depending on whether or not, and then how would you know if it was linear or nonlinear? You would examine the curve. So final momentum, by the way, this is final momentum because the initial momentum is 0. Okay. Student 1 claims that the interaction between carts is elastic. Student 2 claims the interaction between carts is inelastic. It indicate which student is correct. Student 2 is correct. Okay. All right. Why is student 2 correct? Student 2 is correct because the initial kinetic energy of the system was 0, and the final kinetic energy of the system is not 0. So kinetic energy initial of the system is equal to 0. Kinetic energy final of the system does not equal 0. Okay, so this is not elastic. Okay, that's probably all we're going to get through today, but I will make another video for this FRQ number 2, which in my opinion is closer to the type of problem you'll have if you have one on this. The first one was to get our wet our whistle, so to speak.